meeting is now being recorded.
So good afternoon, ladies and gentlemen. It is time to start our monthly seminar. Before I introduce today's speaker, I would like to introduce you to Candice. Candice is my co-worker. She will be hosting the webinar with me. So please send email or whatever question you have to her or to me directly. So today's speaker is Dr. Martis Vasquez. Dr. Vasquez is a senior environmental scientist supervisor with the California Department of Fish and Wildlife Office of Spill Prevention and Response. As supervisor of the Pollution Response section of the OSPR laboratory program, she serves as technical lead for the Water Pollution Control Laboratory Chemistry Program and the laboratory director of the Petroleum Chemistry Laboratory. So with this brief introduction, I will pass the phone line to Martis. Martis, you can go ahead and start now. Thank you for volunteering to do this webinar.
Great. Well, thank you, Deweet, for the invite, and thanks to everybody who's attending the seminar today. And so today I'm going to be talking about some collaborative work that the Water Pollution Control Lab conducted with the California Department of Pesticide Regulation in terms of developing and validating an analytical approach to using continuous low-level aquatic monitoring samplers, or CLAM samplers, for looking for pesticides in urban runoff. And so, again, there's my just cover slide. And the outline of the talk today, we're going to briefly go into just talk about how organic sampling for pesticides is traditionally done using the grab sampling approach and some of the issues associated with that. And then we're going to talk about using an alternative approach for sampling pesticides in the aquatic environment, and this is using the CLAM approach. We'll talk about some of the advantages and limitations of using the CLAM approach, and then we'll get into the laboratory method development that we did, and I'll show you some of the validation data we generated, and briefly talk about some of the remaining issues that we didn't quite resolve, but could be resolved in the future. And then finally, I'll finish with talking about DPR's work. They did some field test cases using the CLAM sampler that ultimately used the validated method that the laboratory developed for them. So with that, we'll get into it. And so usually in traditional water quality monitoring programs, organic samples, organic constituents, including pesticides, are usually collected using a grab sampling approach. And one of the issues with this approach is that it's easy to miss pulse events. So depending on when you're out sampling and when some of these pesticides may be coming through, you know, if you're not out there at the right place and right time, you may miss it. Or the fact that maybe the levels are at such low levels that you may not be able to detect them using the grab sampling approach. Another issue with grab sampling comes down to just logistical limitations of collecting a sample size. So traditionally, the lab asks for 1 liter water samples to screen for pesticides. One of these things can be that can be, depending on how many sites are collected, that can be a lot of water for a field crew to get back out of the field. And then in terms of shipping, those amber glass bottles are prone to breakage, so that can be an issue in terms of shipping samples. Also that it's very costly to ship a lot of water samples. And then just generally in the lab, you know, there's only a certain volume. A lab is going to have a hard time handling 20 liters of a water sample to process. So those are just some limitations associated with grab sampling. The other thing to think about is in terms of grab sampling is that fixed sample volume is going to ultimately dictate the detection limits that you're able to achieve. So ideally, yeah, we want to have as much sample as we can get, so then we have as much analyte mass to work with, and then it's more possible for our instruments to see something. But So a limited sample volume, that's ultimately going to limit your detection limits. So if we talk about using an alternative approach, we can, such as the CLAM approach, we can maybe overcome some of these issues. So the CLAM, sorry, my phone is all ringing. So what is the CLAM? The CLAM sampling device is shown here. It's in the upper right-hand corner. It is a low-flow active sampling device. It consists of a solid phase extraction cartridge housed in a nylon body with a low-flow pump. And you can see the actual extraction cartridge is shown in the bottom right-hand corner here. And the idea with this is that water is pumped through this cartridge at a known flow rate, and analytes that have an affinity for the particular sorbent in that SPE cartridge can be sequestered on that sorbent, and then ultimately after the deployment period, the cartridge is removed from the sampler, and then that cartridge itself is what is submitted to the laboratory. These solid phase extraction cartridges are available in different sorbent phases. So for instance, the work that we did, we used an HLB sorbent, which stands for hydrophilic and lipophilic balanced sorbent. There's also other sorbent types, such as a C18 that people may have heard of. That's more of a nonpolar phase to capture more hydrophobic compounds in the environment. But for this work, we did use an HLB cartridge. This CLAM unit is intended to be deployed from hours to days at a measured flow rate. So the idea being is that you would measure the flow rate coming through that cartridge before, ideally during and after the deployment period. So if you have a flow rate, using an average flow rate, and you know the time that's deployed, you can calculate the volume of water that went through there. So the laboratory can tell you how much mass was stuck on that filter for particular analytes, and then with the field data of knowing the volume that was pumped through, you can calculate a time-weighted average concentration based on that information. Some of the advantages of using a CLAM approach is that, as I mentioned, it results in a time-weighted average concentration, so it's an integrative sampling device. So you put it out there over a time period, and then you're going to be sampling whatever's coming through over that time course. The idea with the CLAM, one of the main advantages is that you're pumping a large sample volume through this, which ultimately is going to get you the lower detection limit. So if you pump 40 liters of water through this, that's 40 times more sample than you would be getting if you just submit a 1 liter grab sample. And then you have that the mass collected over that whole time period. So that's giving you that integrated sample. This approach is really useful as a screening tool to determine which contaminants should be targeted for traditional monitoring. So maybe in your traditional monitoring approaches, like you're not able to see the low levels that you need. So maybe you're not quite aware of what all residues are present in your water body of concern. And this is a tool that can help give you some of that preliminary information of, oh, this is, we are getting detections of this, and let me look at the use patterns and all those types of factors that go into determining how to think about why a compound you're detecting that in your aquatic environment that you're interested in. Some of the limitations of the CLAM approach is everything's going to have some limitations. There are some, it's possible for the cartridge to foul over the deployment period. So let's say you're in turbid waters or there's a lot of sediment. The cartridge itself can plug, and that can be an issue if over your deployment period that flow rate changes because the cartridge is plugging. So that can be an issue. Also determining accurate flow rates, as if you're having changes in the flow rate over time, or you're just actually trying to measure that is something, that your volume calculation is only going to be as good as that flow rate measurement that you get. And I know the manufacturer is working on some kinds of devices, or specifically a volume totalizer, which helps you get at that accurate volume determination. Another consideration to think about is that the concentrations determined from the CLAM sampler do not always translate into exposure concentrations. So again, that concentration that you're going to be calculating is a time-weighted average. It doesn't mean that over that entire time period that that was a steady concentration in the water body. So comparing that type of information to toxicity data where you are looking at exposure, like effects levels that are based on constant exposure to a particular concentration, that's just something to be aware of. And depending on how this concentration data may not fit into traditional water quality assessment approaches for similar reasons that I just mentioned. So it's just important for the users of the data to understand the best way to kind of use this in more traditional assessments. So with that background and just kind of the introduction to what the CLAM is, we'll get into the actual specifics of the method validation work that we did in collaboration with DPR. So originally the project objectives, they were looking for us to validate a specific suite of urban use pesticides using an HLB disc. And as I mentioned previously, the HLB cartridge was the phase that was chosen. It stands for hydrophilic and lipophilic balanced sorbent. So it's intended to target a broad range of compound polarities in the environment. So from compounds that are pretty water soluble to compounds that are not very water soluble, to try to get at a broad suite. And they had given us a list of specific compounds, so this is a targeted approach. The other thing is that we wanted to try to design, because we're trying to target a broad range of compounds in the environment, a lot of these compounds some compounds are best analyzed using gas chromatography, some are best analyzed using liquid chromatography. So one of the challenges is to try to do an extraction off of this cartridge that we could develop that would be amenable for compounds that were analyzed either by gas chromatography or liquid chromatography. So that was the original wish list, basically to get as many compounds as possible off of this cartridge and then take it through different instrumentations for analysis. So shown here is the original, DPR's original wish list of urban use pesticides that they had targeted for analysis using the CLAM approach. And so I have this broken down. On the left-hand side, you can see the target analytes that are analyzed by GC-MSMS at the laboratory, and this consists of the pyrethroid insecticide class of compounds. The LC-MS target analyte list consists of both insecticides and herbicides. You can notice that there's a couple organophosphorus pesticides in there, such as chlorpyrifos and diazinon. We do have the insecticide class fipronils with all the degradates included. We also have the imidacloprid, the most heavily used neonicotinoid, is in the target compound list for LC compounds. And then we also had some acidic herbicide compounds, triclopyr, imazapyr, 2,4-D, that were also included in the LCMS target analyte wish list. One thing to note is that all these compounds together with the pyrethroids and all the other herbicides and insecticides on here span 6 orders of magnitude of solubility range. So it's a huge range of compound polarities that we were trying to get. And then on the right-hand side of the screen, I have a couple compounds. They're mostly isotopically labeled compounds that we wanted to use as field surrogates. So the idea being that we would spike that HLB cartridge with some known compounds that wouldn't be found in the environment and prior to deployment, and so we would be able to have a measure of analyte loss upon deployment. So that's the idea of the field surrogate compounds. We also wanted to have a lab surrogate compound that we would add to the cartridge after it had been deployed out in the field and sent back to the laboratory. We would spike this compound, the atrazine label, prior to extraction. So we would have something that would be a measure of analyte loss upon extraction in the laboratory. So we had some QA elements in addition to trying to just validate the wish list of target analytes. So our approach in developing the extraction method to try to get all these compounds, it was a real big give and take. So the idea being we would prepare 1 liter water samples in the laboratory. We would spike all of these compounds, all the target analytes, into the water. We would load that water onto the disc and then go through a series of tests of trying to elute all those compounds off with different solvents, either single solvents, combinations, and then also stepwise elution profiles of various solvent schemes to try to get at all these different compounds. So in general, the more polar solvents that we use to elute that cartridge, such as methanol, acetonitrile, and combinations of the methanol and acetonitrile, as you might expect, we got low recovery for the pyrethroids, but we generally got good recovery for the LC compounds. And just in terms of our threshold for what was considered good recovery was a 70% recovery of what we spiked on there. If we could recover 70%, we thought that was going to be acceptable for moving forward with validation. Another thing that we noted was that the acidic herbicide compounds, unless we pre-acidified that water prior to loading onto the cartridge, we were getting low recoveries. So one of the things with this is in the laboratory, if you submit a water sample, the lab can modify the water sample to optimize analyte recovery during the extraction for compounds such as acidic herbicides. But if you don't have that, if the laboratory isn't able to do that and you're just relying on the pH of the sample and the environment, you're not going to get good recoveries. You may recover what ultimately is available to bind onto the sorbent, but in terms of looking at did I get 100% of what I put in, that's not going to be the case unless we had acidified. So that was something that we noted. So when we were trying to do a give and take to try to see if we could get better recovery for the pyrethroids without compromising the recovery for the LC compounds, we moved to more intermediate polarity solvents such as ethyl acetate. But we got better recovery of the pyrethroids, but we were losing recoveries of the LC compounds. So working with DPR, it was kind of like this give and take is like, we got this compound, but we lost this one. We got this, we lost that. So it was more of a big back and forth of kind of like, what do you guys want to, which ones do you really want? So this is when kind of, the idea of the wish list it was more of like the reality list. We decided at a certain point to stop trying to get the pyrethroids off of that HLB disc, and we thought that using a different phase, such as C18, a more nonpolar disc, might be better to pursue the pyrethroids on. So we decided to go ahead and forego trying to get the pyrethroids and all those LC compounds off the HLB disc and just move forward with the HLB validation and try for the pyrethroids a little bit later. So ultimately, the validated protocol that we settled on was using that HLB cartridge. We would elute that cartridge with 50 mils of a solution of 50/50 acetonitrile and methanol, and we would do 2 times 50 mils. So once we had the eluate, we would rotovap that down to 2 to 3 mils. We would then bring that 2 to 3 mils up to a final volume with methanol to a 10 mil mark. And then ultimately that 10 mil final extract volume would be analyzed using LC triple quad. And again, this validated protocol did not include the pyrethroids. We did not include the acidic herbicides for the reasons I mentioned previously. We didn't get good recoveries. And then we also had to drop malathion because we couldn't reach that 70% mark repeatedly. So this is ultimately the summary of the validated extraction protocol that we settled on. So here is the final target analyte list that we were able to confirm and validate, as well as the resulting detection and reporting limits that we determined. And I just want to point out that these MDL and RL values are based on a 1 liter sample size. So if you are going to pull 40 liters through that cartridge, these values are going to drop by a factor of 40. So in that regard, the more sample volume you have, the more likely you're going to be able to get in the very low part per trillion range, if not lower. The field surrogates also that we finally settled on that became part of the final validated method were the simazine D10 and the labeled fipronil compound, and then the laboratory surrogate, the atrazine label compound. So once we decided on the validated list and did the detection limit studies, we wanted to look at the recoveries of all these compounds over a broad concentration range. So this graph is showing you the percent recovery of each of the compounds. When we took 1 liter water samples, we spiked 3 replicates each at 2, 5, 10, 20, and 100 times the reporting limits I showed you in the previous slide. So with that, you can see all of the compounds had greater than a 70% recovery for all those replicates at all the concentration ranges. So this was something where we felt like, okay, this is robust enough over this concentration range to move out into the field and feel good about the lab's ability to detect these compounds. Once we had finished the recovery study, we wanted to conduct a stability study to determine, okay, once we have these discs in-house, or the cartridges in-house, how long can we keep these in the refrigerator before they need to be extracted? So basically, what's the holding time from the field to extraction at the lab? So basically, we set up a time course where we would analyze multiple replicates at various time points. So at day 0, 7, 28, and 60 days post-spiking. So we took replicates water samples, 1 liter water samples. We spiked at 10 times the reporting limit in 3 replicates. In 12 replicates. We loaded all of those onto the cartridges, and then we put them all in the refrigerator and then pulled them out, 3 replicates out at a specific time point. So this graph that I'm showing you is the percent recovery of each of these compounds over the 60-day time course. And this first graph is just showing you, just for ease of visualization, I just have half of the compounds on this graph, and the next graph has the second half of the compounds. So as you can see, by day 60, we've dropped below pretty much a 70% mark for quite a bit of these compounds. 28 days, we're pretty much thinking that that's okay. For this particular subset of compounds, you can see that includes the fipronils and the degradates. These compounds were stable on the cartridge out to day 60, and that was our last time point. We didn't go any further. So, but because we wanted to determine, the worst performer was going to be where we had to cut off the time course to determine, okay, this is going to be the ultimate holding time. So from the previous slide, we looked at, it was determined that the 28-day mark was going to be the holding time. So these samples need to be extracted within 28 days to ensure that we weren't having compound loss. So that's what we determined with the stability study. So that kind of shows you the validation data of everything for the HLB cartridge. And then I just wanted to show you briefly what type of recoveries we were looking at when we looked at eluting the pyrethroid compounds using ethyl acetate off of a C18 cartridge. And that was where we were kind of like thinking that this is the way that you would want to go. for the future and trying to get these pyrethroid compounds. And just to show you the recoveries, we were looking at between 40 and 60% recoveries, depending on which individual pyrethroid compound you're looking on. And I would just say that with more work and kind of figuring out where we were losing mass at, it's very likely that these pyrethroids could get optimized on a C18 cartridge. So we are trying to, you know, as with anything, you start big, you have very lofty goals, and, you know, you start with a big wish list and then you end up with your reality. So that's very much true for this project. So in terms of just the method conclusions, that we were only able to validate a subset of the wish list, but that validated method still proved to be very useful. With more effort, this pyrethroid could likely be validated off of the C18 cartridge. So just quickly, I wanted to just give you a brief overview of the DPR field study. So they did multiple deployments during non-rain events in Folsom, California, at an area which receives quite a bit of urban runoff. And then they also did a deployment in one storm event in Southern California. So for the non-rain event, they deployed side-by-side samplers to look at reproducibility, and then the laboratory analyzed those side-by-side cartridges. And what we found that the differences between those field duplicates was actually pretty good. We were seeing a relative percent difference of less than 25% for all compounds in those field duplicates for compounds that were detected. We did see some loss of those field surrogates upon deployment, depending on how much volume was moved through there. And we also did see, depending on how much volume was moved through there and how much matrix was actually stuck on those cartridges, we did see some effects on our instrumentation in terms of analyte suppression due to probably matrix effects. They did do some concurrent grab sampling with the CLAM deployments, and they did find that there were lower reporting limits compared to achieved with the CLAM sampler compared to the grab samples, and that they were able to detect fipronil and the fipronil degradate as well as imidacloprid in the CLAM samplers, but not in those grab samples. So that was something that they hadn't seen before in this particular area, but with the CLAM they were able to pick these up. And the Southern California storm event, they wanted to look at the effect of runoff on the sampling, the extraction, and the analysis, and they did run into some problems that needed some more work in terms of clogging with the sediment load from the storm runoff. And then what we saw in the laboratory, because of that clogging and kind of junking up of the cartridge, we did see some low surrogate recoveries and some additional matrix effects on our instrumentation. In general, there was good reproducibility in the rain events and the non-rain events, but the storm event did present some challenges that would require the field crew to do a little more work. The CLAM resulted in lower detection limits and a greater number of detections compared to the grab samples. And based on our surrogate data, we did see that there was possible breakthrough or compound loss in those field surrogates upon deployment. So that was something to note. So in conclusion, the CLAM is an integrative sampling approach that can achieve lower detection limits compared to grab samples in general, depending on how much volume you're getting through there. It's ideal for determining what should be targeted for monitoring. It's not without its own limitations or issues, as with anything, but it may not necessarily be a replacement for grab sampling, but it's something that used in conjunction can be a very powerful tool in your monitoring toolbox. So with that, I'd like to thank DPR for the collaborative work and their support, and then Cindy Sai, Sarah, and Rafia Mohammed from the laboratory for their analytical work that they performed to complete this project. So, and thank you for your attention.
Yeah. Thank you, Martis. People on the phone, we are going to unmute you. You can go ahead and ask a question. If you guys in this room have questions in the meantime, please.
All guests have been unmuted.
Okay. Do you have any question with the box? No?
Hey, Martis. This is Rob.
Yeah.
I just had a...
Hey, Rob.
How are you?
Good, thanks. How you doing?
I have a follow-up question. I know you were doing some work with the CLAM for another group looking at glyphosate, and I just wondered how the recovery was for that compound?
You know, we actually didn't do glyphosate.
Oh, you didn't?
For 'em. No, So I don't have an update.
Okay.
This is Tony. In the stability study, I was just wondering if that's a common thing that you find in something like this where I think it was chlorpyrifos and one of the fipronil degradants, the recovery went up between 28 days and 60 days. Do you know why it would do that?
I think that's more a product of the variation within the actual analysis itself.
Oh, okay.
And not that I think that that's part of just the variation, the analytical variation.
Okay. All right. Thanks.
Sure, thanks.
So can you conclude from your study now, from what you show in the Southern California, that we can detect more compounds with the sampler than the glove sampling?
Well, I think it depends. If you can get the volume of water through there that you need to without having, I know there's filters that can be used, like pre-filters that can be used on these samplers, but basically so that you can actually just have continue to collect a volume of water through there, because basically, that's kind of the name of the game is more volume, more mass on that cartridge, the more likely you're going to detect it, but if your cartridge fouls or you just have that type of issue, and depending on the runoff, that's just going to be something that you're going to have to tackle with. But theoretically, yes, you should be able to capture more mass than you would in a grab sample alone, and assuming that compound is, your instrumentation is sensitive for that particular compound.
Any more questions? We are almost about out of time. If you have one or two questions, I think we can entertain. Any question from the phone? Okay, I think that would be it. Thank you, Marty, for doing this, and thank you all for participating. We'll see you next month, and we'll announce our webinar the usual way. Thank you all.
Thank you. Thank you.
Thank you.
Thank you. Bye-bye.